Okay, so we've been talking about light acting as a particle, and we've been talking about, we were just talking about how Galileo used the concept of lenses, which we saw um, designing lenses, and if you do the laser and jello optics extra fun thing, you will see straight lines, you will see light acting as straight lines as it goes through different things. So all this stuff leading up to this point, we have light is acting as a particle. And if you're in my Newton class, we haven't gotten to our Newton units yet. But in our Newton units, we will learn that Newton had many scientific adversaries, and one of them was a man named Huygens. And Huygens was all about light being a wave. So Huygens is a contemporary of Newton. Isaac Newton is born the year Galileo dies, to give you some sense of where we are in time, which is 1,000 years after Aristotle and more than 1,500 years after Thales. Huygens says light has to be a wave and that we can see that light is a wave just by being inside any dark room when the door is open. Because if light were only particles, when the door was opened, we would see only the straight line things that we see in the camera obscura. But we don't. We see the light spreading out. We see it, what would explain the light bending around the corners. And Huygens knows, because he sees waves, ocean waves, refracting and diffracting. I'm going to pause just a second to get you guys some pictures of those. Okay, so I pulled up some, I realized that I had better pictures of this. This is definitely something we talk a great deal about in our Einstein class. So I'm taking some pictures from, or some slides from our Einstein lecture. Um, so we see light doing this thing where it bends at openings. We see waves doing this in the physical world. And so Huygens and others are able to see water waves doing this behavior that would result in like light coming through and spreading out. So here is diffraction. Here is diffraction where where the wave, not light wave, but where the ocean waves are bending around objects. They come around this side and then they interfere with each other. This is called interference when the wave patterns are over each other. We're going to talk about that a little bit more. They probably wouldn't have seen this because you have to see it from space, but this is a wave refraction in air. So they're able to look. People in Huygens' time are able to understand diffraction of waves because they're able to see what ocean waves do, and they see light operating in the same way. And Huygens comes to the conclusion that light is a wave. Newton doesn't believe this is true. He's very much in line with the particle, and he calls the particle corpuscles. And he spends a great deal of his time arguing with Huygens about this and just absolutely being sure that light is a particle. That light is a particle. And in our Einstein class, in our second semester, we're going to spend a lot of time talking about some of the trouble Newton had with that theory when we talk about Feynman's book QED, which is all about how light interacts with matter. But for this class, for this lecture, let's talk about waves interacting with waves. So in this case, just pretend that these are ocean waves. So here we have two ocean waves, and they're happening one on top of the other. And so think about this as like this kind of ocean wave coming here and this kind of ocean wave coming here, and both waves are trying to act on a single particle of water at the same time. And so what happens when waves do that? Well, we get positive and negative interference, and it's kind of going to look like Newton is a little bit right, because we're going to talk about this as particles changing position, but we'll see in a little bit. So if we were to divide up this into little tiny what's happening at this particle of the ocean wave and what's happening for this particle of the ocean wave. And we were to march along, what we can do is we can add up at each point. Here we have 0 and 1, so that adds together to be the yellow, which is 1. Here we have a little bit more than 0, and it's coming down, but it's still, this is a little bit more than 1. Oh, it's still up there. And so each time we add these two together, and what we get, this is how waves act. They add up. So what we get here, this is constructive interference, where what we would see in the wave is higher than either of the two. And then as they come down, we're going to get destructive interference. Where the wave is going to be lower than either of the two. The wave is going to end up lower than either of the two. So it has a bright spot. If this is light, it has a bright spot and it has a dark spot. A man named, without using lasers, a man named Thomas Young did an experiment where he showed these bands, these bright bands and dark bands. And this was shortly after Huygens, so it's well before Einstein. And this was said in the scientific community to have established once and for all that light is a wave. And so when Einstein comes along, and a man named Max Planck has a problem in something called the ultraviolet catastrophe, which we learn about in the Einstein book, where they can't figure out the math to make it all work out. And Max Planck says, well, you have to treat it as if light comes out in little buckets of energy. But it's just a math trick, he says. Einstein comes along and says, that's not just a math trick. Light is a particle. So it takes us a while till Einstein gets here in around 1905 for Einstein to say light is both a particle and a wave. So if it's a particle, when it goes through a single slit, like Newton said with corpuscles, if it's a particle like these balls shown here in the video linked, we would expect a single slit to show up. And if we had two slits, so light is going through two slits, we would expect to see, if it's a particle, we would expect to see two slits on the target, because the particles are being shot through here and there's two slits. That is not what we see. What we see are bands of interference. So what we see is that we see a whole smear of these. You'll see one bright spot in the middle, but then you see these really bright spots and these really dark stripes going through. And that's what we see when we put the light through two slits. And there's instructions on how to do this in your packet. If you have a cheap laser, there you can get them for like $2 at a hardware store. Okay, now there's something even weirder, which it has to do with the quantum weirdness that we're studying in the Einstein book. And that is, scientists said, well, okay, I want to know photon by photon, which slit does it actually go through? So they put an observer, and in this video, they make it look like the observer is before the slit. Here's the magic part. It doesn't matter if the observer is before the slit or after the slit. And that's kind of the crazy thing. But once you have an observer that can tell which photon by photon, which stripe it went through, all of a sudden the photons stop acting like waves and start acting like particles. When you observe which slit it goes through, your bands will disappear. This is called the quantum eraser. And the crazy thing about it is, if you do it before they go through the slits or after they go through the slits, their behavior at the slit will change. There's a big controversy about this right now. One interpretation is called the Copenhagen interpretation, which says that information might be traveling backward through time. But there are alternates to the Copenhagen interpretation that don't require information to travel backward in time for this to occur. So it's a very exciting time in physics. In your optics packet, there is instructions on how to do this with an inexpensive laser and some soot and a pin. So have fun doing some quantum mechanics maybe. Hope you